Thank you. Um, and what I'm going to talk about, maybe better half, is some work I've done and presented in Grenoble 2 summers ago, but it's also augmented by some recent work and for inversion with partial data. And I will hint how this extends even for the scattering case. So I will start with the radiating transfer model. Then I will talk about Bougain's theory of analyticity. Then inversion from full boundary data in the presence of scattering. Then inversion from partial data in the attenuated X-ray transform, so no scattering. And then I will present some numerical results. And if time permits, just some ingredients of the proof. So the geometric setup, there is a domain in general convex, and in blue, this the support of a source F that is unknown, and we want to reconstruct F quantitatively from exiting radiation at the boundary. This is for the full boundary case. For the partial data case, at least I will present results which are non-scattered, but data will be confined on an arc lambda, and we will only ask the reconstruction of the source that's inside the convex hull. So just in this omega plus. And then I will also hope to convince you how this works, even though there is scattering. Now, the mathematical model is the stationary linearized Boltzmann, which is a balance equation on the density of particles at the point x moving in the direction theta, and the rate of change on the line in the direction theta gets affected by some attenuation. The particles are generated by a source, and there is a scattering component which takes particles from direction theta primes and brings them to the direction theta, and the operator is accounting for all such. The forward boundary value problem assumes the equation, and the one we consider here is for the incoming part of the boundary. These are points on the boundary and directions pointing inside. The ones for which the angle with the normal, with the outer normal is obtuse. So there is no sources coming outside. This boundary value problem is being long studied, and I'll give some of the results on Wellpostness. Results Vladimirov, Ingrid and Simon, Romanov, Lautré and Lyons, Claude Bardot, Michel Cessna. So it's quite well known. In general, there are two types of assumptions: admissibility on the components, which is somewhat natural. And then there is an assumption of subcriticality, which can be understood in the sense that we do have particles that scatter, and there is no generation of particles. So the absorption is larger than the totality of this kernel. Now, somewhat different approaches assume, so these assumptions would generate some Neumann type arguments, and different approach are seeing scattering as a smoothing operator and then some compact perturbation, Fredholm theory. And I would like to mention the results of Mokhtar Karoubi based on averaging lemma, and perhaps the most general Wellpostness result of generic type by Stefanov and Ullmann from 2008, which only requires the sources in L2 and the solutions then are in L2. The downside is that it's of the generic type, but is the most general existence and uniqueness result, and they also give us stability. Now, for the problem we are interested in, we assume the Wellpostness, and what is given the attenuation and is given the scattering kernel. And we are also measuring the exiting fluxes, so U, on the parts of the boundary and exiting directions. Now, this problem has also been studied for quite a while. The special cases, like one-dimensional Larsen and Sievert for layer media. I'd like also to mention a result by Panchenko, where he's not doing the transport, but he's doing something called the Dyson equation. It's a diffusive type approach. But still, it's an important result. Then for the transport inverse sources problems, I like to mention the results of Antiev Bondarenko, and then results in Riemannian settings, starting with the work of Sharafutdinov, and continuing. So there are important results here that I'm not mentioning. I would just stick with Euclidean results, which the talk is considering. For weakly anisotropic media, there was a result by Guillaume and myself, which provides an iterative scheme and and finally, then the result of Stefanov and Ullmann, which in the same paper where they proved the generic Wellpostness, they also have a stability result for reconstructing the source F. It's not yet implemented in numerical reconstruction. And what I'm going to show you, I'll also show you some numerical results which were obtained with the merit of my collaborator Hiroshi Fujiwara. And last, I would mention a fairly recent result by Klibanov and collaborators, where they consider reconstruction in a slab geometry, where measurements are done on both sides of the slab. So for the result, that partial data result, it would amount to measurements on just one side of the slab. So more specifically, the Guillaume's and myself's result says that if the scattering kernel the anisotropic part of the scattering kernel is sufficiently small, then the U on gamma plus recovers the source. And this has actually an algorithmic type proof where you could consider an iterations and the Neumann type inversion would hold. The generic stability result of Stefanov and Ullmann considers the adjoint of the X-ray and have a stability estimate of the L2 norm of F based on this normal X star X on a larger, on a super domain. And the arguments are, again, compact perturbation of the non-attenuated, the non-scattering case. So I sub A would stand for attenuated X-ray transform. Now this results, this did provide an iterative reconstruction of the Neumann or Fredholm type. I have not seen the Stefanov-Ullmann's result implemented, but I would assume some iterative reconstruction of Fredholm type can be done. Now I'm going to give a brief overview of Bourgain's theory of analyticity he developed for the computerized tomography problem. And okay, so I'm going to come back to the transport equation written in red here. And in 2 dimensions, so this is specific to 2 dimensions, and I am not aware if there are any extensions to 3D. The advection operator, the differentiation in the direction of theta, has a nice decomposition in the, as a sum of d bar and d operators. So if we look at the density of particles decomposed in the angular variable in the Fourier series, and for real valued sources and real valued coefficients, we have a real valued density of particles. So just looking at either positive or negative nodes suffices. I'm going to follow the development of Bourgain for where he uses negative modes. So it's gonna be a little bit strange, but it's for people that know the theory very well, maybe easier to follow. So if we plug this and into the equation, then the new equation for the non-negative, non-positive Fourier modes of the density of particles, now we replace the angular component by a sequence, becomes a Beltrami system. So d bar u L2, this is the double left translation of sequences, du. Then there is a term, zero order term due to the attenuation. And there is another zero order term due to the scattering. And now I have to stress that what I'm doing and this theory works for scattering media whose scattering kernel is dependent just on the angle between 2 directions and not on 2 different directions. In fact, the very last remark that I'm going to make, it's only possible for scatterings that are dependent on the angle only, and it will be completely wrong to even try to recover source from one side if you allow two independent directions. So this assumption, it is important. In algebraically, the scattering operator becomes a Fourier multiplier of this type. Okay. Now, if in the classical X-ray problem, there is no attenuation, there is no scattering, then the Beltrami equations becomes d bar u plus L2 du equals 0. U is a sequence value function, and d bar and d are the Cauchy-Riemann operators. And this is the starting point of Alexander book game. He showed that solutions to these equations are have properties very much like analytic functions. In particular, there is a Cauchy integral formula which recovers the solutions inside from the traces on the boundary. So here gamma is the boundary, the full boundary of the domain. And this is how we bring information from the boundary, radiation coming outside, to the solution inside. Okay. Now, next order of difficulty is the attenuated case, also solved in this setting by Alexander Bookgame and collaborators. And it's perhaps the place here to mention that there is a completely different approach by Novikov and Roman Novikov, and that's been very productive. So, for example, there are reconstruction based on by Leonid Kumiansky. And anyway, we follow the approach of Bouguer, where he noted that there is an integrating factor that makes the attenuated case equivalent under some assumptions on regularity on the attenuation coefficient to the non-attenuated case. Now, this integrating factor, it's basically are Fourier coefficients of e to the minus h. And h is written in this formula. What properties it has? So first of all, if we differentiate in the spatial variable z in the direction of theta, we get a. This term vanishes. And dA is the divergence beam transform of A, so integration on the semi-axis from negative infinity up to a point z in the direction of theta. The important part, the key property that makes the machinery work is that such a function extends analytically in the angular variable theta from the boundary, from S1 to the disk enclosed by S1. So this is crucial. Okay. Also important, not very hard, that this commutes with the left translation. And in fact, the reason Bookgame's theory was not extended so easily to the scattering case is that the Fourier multiplier due to the scattering does not commute with the left translation. So the extension via an integrating factor is not understood. not even now. However, what I will do today, it does extend in a different way for the scattering case. So now we took the transport equation, we had no attenuation, so classical X-ray, then we put attenuation, attenuated X-ray. Now we put scattering. And I'm going to consider the case of scattering coefficients of finite Fourier content. What I mean by that is simply a polynomial in cosine theta has finitely many Fourier modes, basically. Now we will look at the system, the Beltrami system, Buggen-Beltrami system, which is written here component-wise. So there is a first equation that we will not solve, but I want to stress that this first equation here does recover the source once we know everything else. Okay. Then there are a set of equations, finitely many, which have the presence of the attenuation of the scattering. So, but there is no source involved. So it's important that there are no source involved in this finite system, elliptic system. And then there is a tail. And this is the crucial part, that this tail has no scattering because of the finite Fourier content. And basically, if we can invert, in other words, we can determine this Fourier u sub minus n, these terms in the sequence inside the domain from the boundary information, full data here. This is the full data case. So this equation also written in the sequence value map notation is the one here. But the crucial part is that this is inversion of the attenuated X-ray, no scattering problem. Once we have all the coefficients inside, we can come to the system and bootstrap ourselves backwards. So now this will be known inside. We solve the system for u minus n plus 1. Now we would know u minus n plus 1. We can go for u minus n plus 2 and all the way up to u0. And finally, we use this formula to recover Fm. Now, there is, of course, a question, what's happening when there is no, when the scattering kernel doesn't have finite Fourier content. And this is the reason I consider a source, a pseudo source, as if it were, and then we'll give some error estimates compared to the solution with where we take into account all the other modes in the Fourier kernel. Okay. So this is how it is done. So is reduction to the attenuated. From the attenuated to non-attenuated, we use the Cauchy-Buggen formula to bootstrap from the boundary, to go from the boundary inside omega. Then once we are inside omega, we go back using the equivalence from the non-attenuated to the attenuating, recovering u, this modes u sub minus m, u sub minus m minus 1. And then we have to solve recursively Poisson problem with boundary on the on gamma. Okay, and finally, the source is recovered from that first equation once u0 and u minus 1 has been recovered. Okay. Now, as I said, what if it doesn't have finite Fourier content, and we have an error estimate, which I want to stress. So this is the discrepancy between a pseudo source recovered as if K would have finite Fourier content versus what it should be. And I would like to say only this. So there are some terms that only depend on the boundary data, but there is also a term, U is the unknown solution on of the transport equation, respectively the sequence value correspondent. L is the left translation. Now, in the case that we have finite Fourier modes, this C1 can be chosen to be 0. If it is not 0, then although we have a term here, so just disregard this for a second. This term, if we let m to infinity, and u is in any reasonable space, it goes to 0. It's a tail, because this is a left translation. Unfortunately, the estimate has this exponential growing term, coefficient, which unless C1 is 0, is not much of a, we do not get a convergent. Here M is how many modes do we consider in the scattering term. However, if it is a polynomial, as I said, the coefficient decays, and the C1 is 0, so there is no such a term, and what we get is truly a stability estimate. In delta G is the discrepancy on the data. And as I mentioned, if it is not of polynomial type, then there is perhaps there is an optimization problem to choose for an optimal M. And we investigated this in the numerical case. Now, I would like to contrast with the result by Guillaume and myself, that there we say if the anisotropic part is small enough, then there is a convergence result. And this can be recovered here as well. And what we are saying here is the scattering is small in this W11 norm, in the Lipschitz norm, starting from the very first coefficient gamma 1, k sub minus 1. If that's the case, then we can recover the result in the sense that by letting m to infinity, the pseudo source converges to the real source in the L2 sense. There are no estimates, though, of the error. We can at least prove that this goes to 0. Okay, now next I would like to go to see what's happening if the data is only connected on gamma, on lambda. So I'm reminding you the setup. There is a source inside, and we only measure the fluxes on this arc, and we ask something more modest. We are not trying to recover the source everywhere, but at least can we recover the source on this omega plus just in the convex hull of this lambda. And now it is known that this problem has a unique solution. In fact, if we only measure these rays, we can use the support theorem of Bowman and Quinto, which says that if you measure for the analytic attenuation, if you measure for angles that stay uniformly in X, stay above, away from zero, that's enough to get uniqueness. So we would get F restricted to omega plus. It's uniquely determined by this lambda via this unique continuation argument. What I'm going to present, it's again different, and actually this is work under review, also offers a method of reconstruction. And here I should mention that results from partial data, roughly half the data have been known. So I'd like to mention the result by Rulgard and Nu and Fries, and even Guillaume has a partial data result, also roughly half the data in based on Novikov's approach. Yes. So this is the setup. Sorry. Now I will also use the finite Hilbert transform, which has is quite different, has a long history. But the important part is that in L2 has a very peculiar range property, in the sense that it's not another operator. It is, so the range is open and dense in L2, but is proper subset of L2. And has the I times HT, so the I times HT has the spectrum -1, 1. And it is important that to note that 1 or -1, neither end, is in the point spectrum. In particular, the kernel is trivial of identity minus IGT. So this is the classical finite Hilbert transform that will show. Now, the idea, I'll come back to this, give me a second. So the idea is to transfer the data from lambda to L in this analytic equation, and then we would have the data on the boundary of this domain omega plus, and then we would do reconstruction the way we did it for the complete data set, for the entire omega. So the idea is to move the data from lambda to L. And this move would also, in a sense, resolve the radiation, separates the radiation coming from the F in omega plus from the radiation coming from the F in omega minus. Okay, and this is a new result that U on lambda determines U on the chord. And moreover, there is a very nice formula in which U sub n is the unique solution of this equation, where the right-hand side is determined on the boundary data on lambda. So everything on the right-hand side only accounts for the radiation U on the zeta. Now, the idea of proof, it really follows directly for something that Kamran, my former student, did back in his PhD thesis, where he characterizes the range in terms of Hilbert transform associated with the analytic maps. And basically, roughly saying, so if we leave out all the notation, the result is that U at the boundary is the trace of an analytic function if and only if range is in this kernel. And I want to mention that this is the book game Hilbert transform. So the Hilbert transform that occurs naturally with respect to analytic maps. And the observation which makes this possible is that on the part on the boundary for which I is so on L, that's real valued, and the part where psi is real valued, this term drops out. So if both psi and zeta are real valued, so this observation allows to recover this equation, where now Fn is determined by the data on lambda only. Okay, so now what's happening? So that's it. So we would read, this would solve, I will show numerical reconstructions in the scattering case that we discussed first, but also in the non-scattering with partial data. But what I want to say next is that this idea actually recovers sources. Let me go back. Recover sources F on omega plus in the presence of scattering. This is a uniqueness result, what I'm going to say. And we are currently working to the numerics, and I'll explain where the difficulties are. Now, of course, if the scattering depends on two independent directions, this is not possible because we can cook up a K such that at any point X, we make everything that comes from these directions to move down. So that data is not recovered. In that, what makes this work is that the scattering depends only on the angle between two directions. Moreover, we only have the uniqueness for finite Fourier content. So scattering kernels which are polynomials in the cosine of the angle. So let me explain how this goes. And perhaps this idea would extend to other settings I know of work of Monard and Guillaume, and they in the simple Riemannian metrics. So I'm coming back to the system, and I want to stress, so this is the attenuated X-ray transform. You look at this and just think attenuated X-ray transform. Now, the difference is that the data is only on an arc, lambda. However, we only want to recover it in omega plus. So we can solve this using the attenuated case that I just mentioned and recover all of these coefficients up to omega plus. Now we go back, we know everything here. but we need to solve a D-bar problem with data on a part of an arc. Now, this uniqueness is clear. However, numerically, it's yet challenging. Okay, so that in principle can be done, and then you bootstrap, you go recursively to lower indices. So again, what makes it work is the finite Fourier content, which reduces this to the attenuated X-ray transform. And also our more modest goal to reconstruct the source only in omega plus. Again, this would not be possible if K will depend of two independent directions. We can cook up the K such that everything that comes is gonna be pushed down. So the radiation is not recovered. Now I'm going to present some numerical results. And the first numerical result is for the scattering case, but the data is all around the boundary. We model the scattering kernel by a very well-known and used model in this transport theory, so-called the Henny-Greenstein model. But Henny-Greenstein is usually formulated for 3D, and in 2D, it's simply the Poisson model. Now, what I would like to stress are these numbers. And the reason I stress that is that people write theoretical results and then they don't pay enough attention to the parameters. So G is a measure of anisotropy. So for varying between 0 and 1, G is 1, that's the ballistic regime, there is no scattering. And if it's 0, then the scattering is completely isotropic. The numerical results work somewhere in the middle range, so G is 1/2. But most importantly, the scattering coefficient mu s of z is 5. And I want to stress what that means. This number 5 says that on average, the particle scatters every 1/5 of the path length. So on average, we can see that a particle scatters about 10 times before going outside. So it's far from X-ray, far from broken X-ray or single scattering. But it's also far from a diffusive approximation type of argument. This domain is not diffusive. Now, the simulations are run for the following sources. F is supported in this ball and in the rectangle. And there are two other balls that are dashed here for the attenuation. And the full transport equation is solved, and what you can see here is outside radiation. So at the point of the boundary, the length of this arrow has to do with the value of the radiation coming in this direction. So the fact that they come tangentially at this point is not, it comes from calculation, but it shows that there is no radiation coming in from outside. So all the source is inside. Okay. Also, because they are smooth, this is telling you that there is scattering and also because they don't look the same, it's an indication of non-isotropy. Okay, so this is a reconstruction with attenuation. So there is attenuation, which is written here, It's roughly 2 here, 1 here, and 0.1 everywhere else. Now remember, the source is only contained in here and in the rectangle. So this disk carries two pieces of information. One, there is a source there, and second, the medium happens to have a high attenuation property where that source is located. In this case, the rectangle is the location of the source, and the attenuation, you can see slightly here, is the location of, again, a high region of attenuation. This is the reconstruction that you are looking at now. This is the case where the attenuation was smoothened out, so it's C2 around this boundary in such a way that the discontinuities from the attenuation do not show in the reconstruction. This is the reconstruction for completely discontinuous data, where I would point a difference here. You can tell you can even tell the entire wavefront set, but this is of the attenuation, not of the source, and it shows in the reconstruction of that. That's because if you think roughly that the X-ray, attenuated X-ray is just classical X-ray, but where the discontinuity also comes in the source, then this is an extra discontinuity that the reconstruction show. Also, I like to mention that we need two derivatives in the attenuation in the theory. The numeric is done on the discontinuous coefficients. Oops. Now I'm going to go back to the reconstruction, but this is the non-scattering case, and look how the data looks like. So there is no smoothness. So what you see, these balloons are the same balloons from before, from computed data. And I can enlarge them, something like that. And the pink region are areas of high attenuation, which we assume known. So when we invert the attenuated X-ray transform, but the data is measured only on this arc lambda, what we would like to see is the source F, which has a disk and a rectangle here. This is, you are looking at the attenuation here. And this is computed data. So these balloons come from computation. And now, next I'll show you the reconstruction. So this is the reconstruction of the source F from data only on the arc, is based on solving identity minus IH for along the segment. So inverting this, well, it's not inverting the Hilbert transform, but it's inverting an operator through a point in the continuing spectrum, which is not in the point spectrum. And the results right at L or very near L are not good, but as soon as we are a little bit off, this is what we can reconstruct. So again, this is reconstruction of the attenuated X-ray transform when the data is only on the arc, and we only are interested in the part in the convex hull of the arc. I will stop here. I just want to mention some of the references where this work can be found. this partial inversion is still under review. Thank you.
Thank you very much, Alexandru. Thank you very much for the nice talk. Are there any questions or comments? Please unmute yourself. Any questions or comments, please?
Hi, I had a question.
Please.
Sorry, my video is not on, but I was just wondering about the partial data results that you mentioned. You said that if you have roughly half the data, you can reconstruct the source?
You can, yes.
So
it's more precise than that. So your source is also in the lower half plane. So what you measure here, for example, along this line, you also have contribution of radiation coming from the part under.
Right.
But you do have the data in all directions, exiting directions on an arc. Right. And you can reconstruct in this region, in the upper half plane. The
right, so you reconstruct in the convex hull.
Yes.
And is that true for all the partial data results of this type, or just for the one that you mentioned?
I think this is new. I don't think this is covered by any existing partial data.
Okay, sorry, I thought you mentioned some other partial data results by other authors.
Yes, but not this, they don't cover this case.
Okay.
With again, with the exception of the result, the uniqueness result coming from injectivity result of Bowman and Quinto. So that result, that result is telling you you don't even need to measure in all around the arc, but only measure directions that come and exit on the arc. That's enough to conclude that there is a unique source. But that's a uniqueness result based on unique continuation, based on the fact that the attenuation is real analytic.
Is that just in the convex hull though as well?
Well, in a sense, yes, because you assume that at all points in the domain, you do have this measurement of for this in this cone of angles at any point in the domain.
Okay. So, and is the Bowman and Quinto result with scattering as well?
No, okay. No. But it's not just that. You need to. What I'm trying to say is that they say if through any point of that, if your set of lines is such that at any point it spans a certain cone, that is any point. So if your source is in the lower half plane, you have to have, here you are missing this kind of, right? So if your cone is adjusted for the upper half plane, right? So we are talking these angles. Then you are missing that cone for the points in the source which are in the lower half plane. So you would not, that result does not apply to tell you that you recover in the lower half plane.
I see, yeah.
So they are not equivalent, but if I only look under the modest goal to recover in the convex hull, then yes, I can recover it uniquely, because there the cone is determined, okay?
Mm-hmm.
So, but here, in addition to the fact that actually gives you, is not that if the difference is zero, it's telling you how to recover. And the attenuation is C2, not real analytic.
Okay.
Thank you very much. Are there any other questions or comments? Any other questions or comments? Okay, if not, then thank you, Alexandru, once again for the very nice.
Thank you, Katja, for inviting me.
And thank you very much, everyone, for coming. Thank you.